Good evening, everyone. Welcome to our final session in Theater 14 today. I have the pleasure of introducing Vlad. Take it away.
Thank you. Hello, everyone, and welcome. I'm Vlad Iliushin. I have been in cybersecurity for over a decade. Now, my journey started at Samsung Electronics. Then I moved to a company called Avast, which is a AV vendor, where I helped to found and manage the IoT lab, which was the lab with focus on the IoT and network security threats. And now I work for Elio, where focus is the same as mine, which is cyber deception, that is you honeypots and honeynets, as well as mass exploitation and network reconnaissance, which is usually can be a first step in the attack kill chain. With that said, you probably can see that I like network security and I like networking. And networking is simple for some people. For others, it is absolute nightmare. What I meant to say is that networking is simple. In 1969, somebody came up with the very first RFC, or request for comments, and everything was peachy since then. Except networking is not so simple. In 1981, the very first RFC describing TCP standard was published, and that means that the TCP was around for longer than many people in the audience have been alive. And with all of those standards and extensions, requests for comments and amendments, networking is simple where it works and not quite so simple where it doesn't. And with that said, wouldn't it be nice if there was a way where you can actually create a characteristics of connections and clients and servers without going to the Wireshark or dumping a pickup every time? Which brings me to fingerprinting, which is just that. It is a characteristic either of some specific connection or server or a client, or just the pipe between point A and point B. With that said, a lot of people like to talk about taxonomy, so let's go over taxonomy of network fingerprints. One way we can put fingerprinting in two different buckets is to describe them as active fingerprinting and passive fingerprinting. Active fingerprinting is where you create some sort of new connection, you introduce new traffic into the system, and you create fingerprints based on some replies. One of the most popular ones would be Nmap and its OS discovery. And passive fingerprints, as opposed to active, they don't require any new connections or any new traffic. You can just sit on the data pipe and create fingerprints for the connection based on the existing traffic. In this presentation, we will be focusing on the passive fingerprinting because it is not noisy and you can go back home into your company, into your enterprise network and start fingerprinting all the things without introducing any nodes or any noise or changing your network stack. Another way to describe fingerprinting is to classify them as the fingerprinting that happens at the start of the connection or fingerprinting that happens continuously. At the start of the connection, you usually take some handshake, for example, TCP three-way handshake or TLS client hello, and you create fingerprints based on just that data. Continuous fingerprinting, on the other hand, happens continuously during the lifetime of the connection, and it can change over time. It is basically some flow-based analysis. In this presentation, we will focus on the start of the connection because usually it is quite deterministic based on the data and doesn't change over time. And finally, you can put different fingerprinting algorithms into buckets based on the OC layer on which they exist. For TCP IP fingerprinting, we put them in one bucket, and for L7 fingerprints like hash or J3 or J4, it is different bucket because it works either on L6 or L7. We will cover both of those buckets. Now, when we're speaking on the about fingerprinting, there are quite a lot of different algorithms. All right, from very first OG like QSO and POF to the modern MuonFP for TCP, and also from JA3, which is OG of the OG of the TLS fingerprinting, all the way to the more modern one like JA4 and JA4+. You can see there are actually JA4 and JA4+, and that is because JA4 is an evolution of TLS-based fingerprinting JA3, and JA4+ is its own suite of different fingerprinting algorithms, like fingerprinting of HTTP connection or connections or SSH connections. JA4 is released under the same PSD3 closed license, just like JA3, and JA4+ is released as a proprietary FOXIO license where source is available, so your mileage in using those fingerprints may vary. In this presentation, we will cover POF and MuonFP for TCP IP fingerprinting, and JA3, J3N, and JA4 for TLS handshake fingerprinting. When we talk about all of those fingerprints, it's important to have a quick refresher of the OC 7-layer model. Anybody sees a problem with this picture? Okay, I see a few hands. Great. So one of the layers is SAS, and specifically in this case, it is the layer that somebody had called Zero Trust. The reason I'm showing this slide is that a lot of people here are at the beginning of their network security journey and are trying to learn. And if you go to your favorite search engine, it is possible that you will find OC 7-layer model described with more layers. Nothing against Zero Trust. We're using it in our company, but it does not belong into the OC 7-layer model. So OC model just describes different or tries to abstract different layers of network communication, starting from the very first, which is bits on the wire, all the way up top to the application layer where application data lives. In this talk, we will cover TCP and IP, which is layer 3 and 4, and also we will go way up into the presentation layer, which is responsible for encryption, and also a little bit sprinkles of application layer. Now, in many cases, people refer to L7 as actually L5, L6, and L7, which is fine because application layer and everything that happens in application, it's very interconnected. So let's move to the TLS handshake. Usually we have a client and a server, and they just want to exchange some data to figure out which way to encrypt underlying traffic. So they negotiate TLS version or ciphers and so on. And TLS handshake fingerprinting is basically based on the client hello for the client and server hello for the server. With that, meet J3, the OG of TLS fingerprinting. As you can see on the slide, it is a long string, which is the IOC that everybody uses. And this string is just a hash, MD5 hash of underlying J3 string or J3 row hash, right? And as you can see, it has 5 parts in total. So let's go over each part. The very first one is the decimal value of the TLS version. So 771 is TLS 1.2, 772 is TLS 1.3, and so on. Then we have cipher suites. It is just a list of cipher suites that client is able to use. And following that, we have the list of extensions. Again, it is just the extensions of that client is able to use in the communication in the TLS level. Following that, we have elliptic curves, also a list, and finally, elliptic curves point formats. With that said, here are 3 JA3 fingerprints of my Chrome browser. I gathered them just by going to the web page that gives me my JA3 fingerprints and refresh the page a few times. And you can see that I got 3 different hashes, 3 different J3 values, which is quite a problem for fingerprinting TLS traffic, where every time you connect, you get very different hash or fingerprint value. So why is that? Let's take a closer look at the J3 strings of all of those 3 connections, and you can see that the first value, the TLS version, is the same. The cipher suits are also the same, they have the same values, and they ordered exactly the same. Going back to the fingerprint row value, elliptic curve point formats are also the same, and so are elliptic curves. So let's forget about them for a second, and let's also get rid of the row hashes. Obviously, if you put different strings in MD5, you will get different values. What is happening here? As you can see, the TLS extensions are exactly the same. They have the same values, but they're ordered differently. And that is because Google Chrome, a few years ago, created a new feature called TLS Extension Shuffle. They did this to circumvent fingerprinting of Chrome browser, which is really helpful. The thing is, if Google knows this, attackers also know this, and they can implement their own randomization of connections, which make this hash quite hard to use. Another small issue that I personally find with J3 is that it has no human-readable part in the hash itself. It is just an MD5 hash of J3 string. So the first lesson learned, if you're doing network fingerprinting and the algorithm that you use for fingerprinting has some raw value, always store this. Because if you build your own IOC database with your sweat and blood and tears, and then a small new feature and small new shuffle will change all the values of your fingerprint, with those raw strings, you can actually just go back in time and start shuffling them as well, or ordering them. But without that, you are kind of out of luck. With that said, there is a small refresher on the J3 of J3 fingerprinting called J3N. And the only difference is that they actually started to sort the TLS extensions to also help with fingerprinting of Chrome browsers and all browsers that started to shuffle the TLS extension part. With that said, meet the new kid on the block called JA4, which is the evolution of TLS fingerprinting created by John Althaus in 2023. And this fingerprint actually has 3 parts. The first one is human readable, and then there are 2 hashes. So let's quickly go over the fingerprint. The very first value is just 1 character, and it represents the way this TLS handshake happened. T is for TLS, Q is for quick, and D is for DTLS. The following 2 characters is human readable TLS version. So 13 is for TLS 1.3, 12 for 1.2, and so on. Then we have an SNI type. D stands for to domain, and I stands to IP. So basically, based on this character, you can quickly see, hey, this connection here actually happened to the domain. And if you have your web server, you can actually quickly distinguish, hey, all those connections are actually happening to the IP address as opposed to domains. Maybe they are not really your proper clients. Following that, we have a cipher count, which is just the count of ciphers that client supports or advertises. And then we have extension count. Finally, we have first application layer protocol negotiation value, which is quite helpful because here you can see, hey, this client wants to communicate over HTTP version 2. Then we have truncated SHA-256 hash of cipher suits, this time sorted. And finally, the last part, it's truncated SHA-256 hash of extensions, which are sorted, and also signature algorithms in order in which they appear. Just like JA3, JA4 has JA4 raw, which is the raw value which is used to create those SHA-256 parts. Right? So in here, it is actually consists of 4 parts. You have human readable part, then you have the part with all the cipher suits, the part of signature algorithm, the part of the extensions right there, which are sorted, and finally you have all the signature algorithms. So it is quite useful if you want to go back and see what is the most popular extension algorithm or cipher that is supported by all the clients in your network. With JA4, you can do a lot of cool things. For example, if you use Archime, which is an open source DPI utility that you can just deploy across all your network, you start collecting JA4 hashes and then see, hey, there are a lot of clusters of multiple IP addresses that use some specific hash. In example here, it is actually NGROC clients who are trying to enumerate your network perimeter. And also, there are multiple detections that you can do in the JA4 space. For example, the first value here is JA4 hash, the second value is JA3 hash for the exact same thing. Depending on the sample or the blog post or the source of your data, it is either Cobalt Strike C2 communication coming out of your network, or TrickBot, or Windows HTTPS interpreter. So if you see this hash in your network, something must go wrong. Going a little bit deeper into the rabbit hole of fingerprinting, let's go to the TCP IP fingerprinting. Just a quick refresher, here is TCP header and TCP data. TCP header is between 20 and 60 bytes, depending on the number of TCP options. And oh boy, do I like options. This is just a quick refresher on the TCP three-way handshake. You have a server, a client that tries to connect to the server. You have SYN, server replies with SYN ACK, and finally you have the final ACK. And usually TCP fingerprinting happens at the very first part of this connection because it has the most interesting data and most characteristic about the client. So meet the OG of TCP fingerprinting, POF, where it's so old school that all is spelled as 0. It is was created by Michal Zalewski all the way back in the year 2000. And on the slide, you can see the typical output of POF2. And below that, you can see the raw signature, which is POF signature, right? It has quite a lot of parts, but they're quite simple. The first one is the value of the IP stack. So 4 is for IPv4, 6 for IPv6. Then there is a TTL value, which is basically number of hops left, so the TTL of the packet that arrived, and also some guessed value based on the typical stack. So if you see 120, obviously you're going to guess, hey, the TTL was probably 128, and there are 8 hops between you and the client. So moving to another value from the IP part of the TCP IP, you have IP option length, because remember, IP packet also have IP options. During the TCP handshake, you should probably see 0. Then we have MSS, or maximum segment size, and window scale, and window size and window scale. In newer version of POF, this value of window size can be represented as a multiplier of maximum segment size. Finally, we have all the TCP options in order in which they appeared in the packet, and IP quirks, so in this case DF for do not fragment, and ID is present. And finally, we have payload size class. In the IP in packet during the TCP three-way handshake, you probably should see payload size of 0 because there are still no data, and 0 is for no data, and plus is for any amount of data. So if you see TCP handshake with plus there, something is going wrong. And on this slide, you can see typical detections, list of detections of POF. And maybe you now start to see the problem why POF is not so widely adopted. Majority of those detections, because POF stands for passive OS fingerprinting, so majority of those detections were created trying to determine which operation system is running on the other end, on the client. And with all those new interesting algorithms with HTTP and all the cookies and all the headers, it became not as used anymore and was not very used for cybersecurity, unfortunately. One of the biggest users of POF is Cloudflare. They released the POF BPF, not eBPF, BPF compiler all the way back in 2016. And they used this compiler to create the rules to basically drop the traffic from the weird devices with weird POF values, and also as a part of their anti-DDoS protection. So meet the new kid on the block, MuonFP, created by Ken Webster in 2024. And from the name Muon, it is quite fast and also very simple. And I do believe we can do with more simple things in cybersecurity. It has just 4 values. Everything is human readable. The first one is window size. Then we have TCP options as kind numbers. Then we have maximum segment size, and finally scale, window scale. Going back to those TCP options, in order in which they appear, in this case we have maximum segment size set, sucks permitted, we have timestamp, and no op, nope. So it is used usually for padding and the TCP header. And finally, we have window scale. Here's another example of very common MuonFP fingerprint with all the options. Any guesses what this can be? Which network stack produced this fingerprint? Anybody? So based on the window size being a multiple of maximum segment size, and the fact that we don't have an 8 in the TCP options, which usually is used by Linux operating systems because they use timestamp option in the TCP stack, it is Windows, and in this case it is Windows 10. Now this is the same fingerprint, right? Except the window size is 65,535, and this time we actually have TCP option 8, which is the timestamp. So in this case, it is an Ubuntu. I know how it pains Arch users here not to say anything. Don't worry, you are able to fingerprint your network stack after the presentation. And here is almost identical fingerprint, and the only change is maximum segment size. And that is because it is the same machine connecting to the server through mobile network of Verizon. You see, Verizon actually needs about 72 bytes of overhead for their communication, so naturally your maximum segment size gets lower. What happens when you try to use our Windows machine and connect through the different proxy servers? Obviously, you have a smaller window size, and you also have a smaller window scale, right? Here is a different proxy, and you can see that window size right now is even lower, but also the scale size is 0. So this is a trap, by the way. If you look into the TCP options, you will see that there is an 8 there, which suggests that it is actually a Linux machine connecting to the server. And the thing with proxies, especially public proxies that you can find on the internet, is that they work a little bit different, because when we fingerprint stuff, we usually fingerprint at the side of the server to fingerprint the client. But when you use the proxy, you're actually fingerprinting the proxy itself and not the client. So just remember where you fingerprint and what you fingerprint. How VPN tunnels can affect the connection. Because usually, let's say you have a client, you have the server. On both sides, you have a network with MTU, maximum transmission units, set to 1500, which is de facto the standard, and you have nothing weird going on between point A or point B. So when you use VPNs, you just encapsulate the underlying TCP stream into something else, which creates overhead. So going back to our favorite Windows 10 machine, this is the fingerprint, and this is the fingerprint of the same machine that actually connects over OpenVPN. So you can see that in this case, the overhead is very not nice, 61 bytes. Then this is the fingerprint of the same machine connecting over the WireGuard, which creates overhead of about 80 bytes. And finally, you have the fingerprint of the same machine connecting using IKE v2, which uses 100 bytes of overhead. Now remember, different implementations, different libraries, and different network setups can create different overhead. I think a lot of different mobile networks will have some sort of semi-unique overhead and semi-unique MSS. And if you actually look into the Windows size part of the fingerprint, the very first one, you can see the Windows network stack at work, because Windows really tries to set the Windows size as a multiplier of maximum segment size. So you can see it here that it is just a multiple of this value. And finally here it really tries to make sure that it is some nice multiplier of the MSS. And the reason for this is that in the RFC and in the specs, it is strongly suggested to use multiples of MSS. Now, here are three very common fingerprints. You have Windows, you have Ubuntu, and you have an iPhone. Let's put them aside for a second. And do you see anything weird with these two fingerprints? So, if you have a public IP address, I can guarantee you that you receive connections with those two fingerprints every hour of every day. So let me help you. The bottom fingerprint, you will see connections from Academy for Internet Research and also French CERT. And top fingerprints, you will find connections from Shadow Server, Rapid7 Sonar, and Binary Edge. Any guesses of what this may be? The first one, you will also find those connections, don't worry. You always will find those connections from threat actors. The first fingerprint is characteristically a ZMAP, and the bottom one is mass scan. You see, scanning the internet is hard. Scanning internet on the scale is very hard, and those two tools actually write their own routines to generate SYN packets very, very fast. And because of that, they don't have many TCP options, because there are no expectations of actually using the connection. You use SYN scanning just to find and knock on all the ports and find which ones are open. Which brings me to the network reconnaissance kill chain. We have first stage is usually port scanning, because you need to find, hey, what is actually open? And then you have service enumeration and discovery. You want to figure out, hey, what is running on those open ports? And you can do it in many different ways. You can use the same server, same IP address. So you have one stage, and this stage basically does both port scanning and also service enumeration, which will result in having two different sets of fingerprints. You will have one set of fingerprints used for fast scanning, and another set of fingerprints used for service discovery, depending on the network discovery engine that you're using. This is, by the way, set of fingerprints used by Shadow Server. Then you can be a little bit different. You can split this routine into the multiple stages. The first one being the port scanning, and then you offload the data from the first stage, take all the open ports, all the IP addresses, and move it to a different server, which will be responsible for service discovery. In this case, you will have two different IP addresses with two different sets of fingerprints. This is, by the way, Shodan, and as you can see, they actually tried to use different sets of fingerprints. They created their network stack for fast scanning to use TCP option of maximum segment size, and they also randomize the window size, which is quite interesting because it really helps to identify Shodan scanning servers, because they usually produce about 38 to 60,000 of unique fingerprints. So if you have some IP address and it is not possible to figure out what this is based on the reverse DNS or static IP lists or something else, you can try fingerprints. But what about the attacker? What happens after reconnaissance? Usually, bad guys like to do something we call initial access, right? And they move to the exploitation. The thing is, advanced actors can afford infrastructure or can afford to rent a botnet to do the scanning of the internet to find targets. But a lot of them prefer not to do that because it's hard, it's expensive, you have to deal with a lot of things. So they use something else. Who here uses Census or Shodan? Okay, great. Who here blocks Census or Shodan? Okay, that's great. So what happens when you don't block Census and Shodan or other scanners is that you get yourself a free attack surface management with one catch, is that the data in this attack surface management are accessible to everyone. So all the bad guys need actually go to public scanner and get the data for targets to exploit. Which brings me to actually combining the IP blocking and fingerprint based blocking. Who here uses IP blocking, just out of curiosity? Okay, the same people. Who here uses fingerprinting blocking or blocking based on the network fingerprints? Okay, amazing. Please find me after the talk. So here you can actually use a combined approach of blocking known stuff or very, very bad malicious stuff based on the IP addresses. For example, Census is quite nice. It will just give you all the IP ranges that you can block. Threat actors, not that nice. You have to figure this for yourself. And then use fingerprint-based blocking for blocking fast scanning and fast scanning activities just based on the fingerprints. So you don't block the IP address, you block just based on the network fingerprint, and that way you are not affecting any other traffic that can be benign coming from the same IP address. You can actually look for combining IP blocking and fingerprinting, and you will find a few blog posts about this. Now, you like fingerprints or you're excited about fingerprints. How do you gather them? Well, with MuonFP, with TCP fingerprints, you can use Rust-based standalone tool and just deploy it to all of your machines. And right now we are working on publishing the Archimi plugin, so you can use it in Archimi. And we're starting to work on the Wireshark plugin, so you can use it during the trainings or workshops, etc. So coming soon, trademarked. With JA4 and JA4+, you can use, again, plugins to Archimi and NTOP and Zik if you like DPI. You can use vendor-specific data, for example, AWS CloudFront. And finally, you can get the fingerprints from the reverse proxies like Cloudflare and Fastly. Unfortunately, they do not support MuonFP yet, but if there are people in the room who are huge enterprise customers of either Cloudflare or Fastly, wink wink, you know what to request next. So how can we, or where can we actually gather fingerprints? This is a very simple example. You have a client, you have a server, and you want to fingerprint the client. So you fingerprint at the server side. It's very simple. With reverse proxies, it's a little bit more complicated because you cannot actually fingerprint at the server side. Otherwise, you would be fingerprinting your own reverse proxy, which is just not as fun. So what you can do is start fingerprinting at the reverse proxy part and forward the fingerprints in the headers downstream where you can capture them. Now, there are many ways to skin the cat, and now there is on-prem infrastructure, there is cloud infrastructure, there is multi-cloud infrastructure, there is hybrid, and if you're a startup, your infrastructure is a laptop and your brain. Fingerprinting the brain waves is out of scope of this talk. So depending on your need, you can start fingerprinting at either the router, or if, for example, you have a huge set of Ansible scripts to manage whole your infrastructure, it makes sense to just deploy them on the server and forward it into your SIEM. So how can you capture some true value from network fingerprinting? Well, the easy path is usually to write more detections. This is just an overly simplified example of detecting fast scanners. This is a Sigma rule that you can push and start creating new detections. In the real world, you probably would have a few stages like enrichment and trying for things to make sure that you have proper data and you don't have too many detections, because trust me, if you actually publish this to production, fast scanning happens every second or every few seconds, so you will be perfect vendor that generated 1 million of alerts that are not that useful. What is more interesting, in my opinion, is to do something with this detection, and this is an ELK example where you can actually write the rule to see if something is scanning your infrastructure and push it into your routers, into your block list, and start blocking this actor. So this is the example of zero first patient detection, where basically if somebody is scanning part of your infrastructure, you detect it and you start blocking on the IP layer across the whole infrastructure. So once this actor moves to other IP ranges or other parts of your infrastructure, they are already blocked. And finally, it is quite fun to use in threat hunting. If your platform supports wildcards, you can use wildcards in fingerprints to start searching for interesting things. And in this example, well, there is absolutely nothing interesting happening, nothing to see here. Finally, I would like to actually thank Ken Webster, creator of MuonFP, and acknowledge his work, as well as Luca Derry, who is the author of open source and top DPI, John Althouse, Jeff Atkinson, and Josh Atkins, creators of JA3, and now John Althouse is working on JA4 and JA4+, Michal Zalewski, creator of POF, Andy Wick, who is the main person behind Alchemy, which is amazing, as well as all contributors and the open source community as a whole, which is extremely helpful to actually achieve something in modern tech stack. So one thing I would like you to live with is that fingerprints are just another tool in your arsenal, and it is up to you to extract the most value. You can start detecting things, you can write detections, you can use it for IOCs, you can use it for blocking. It is up to you. Because remember, ultimately, the security of your network perimeter and your company is in your hands. So that's pretty much it. And I think we have time for questions.
Thanks, everyone. I don't have any questions on Slido. Does anyone have any questions from the audience? I can have you step down. Okay. Otherwise, oh, yes, one moment.
So great presentation. So my question is, can you use network fingerprints to allow list internal applications?
So the last part, sorry.
Can you use network fingerprints to allow list instead of block the internal applications that you use?
You can absolutely do that. The thing with network fingerprints is usually you will have to write some kind of eBPF filter because eBPF is amazing, and you are the owner of the network stack in this case. I have mentioned a few examples where you can just block fast scanning, right? You can absolutely actually use it as a part of XDP or Express Data Path in Linux kernel, and you can start blocking everything that does not pass your filter. So we can absolutely set, hey, I have 3 fingerprints, which is the Windows and Linux. Everything else gets dropped. If you're more into chaos and cyber madness, you can actually start to reply with SYN-ACK to every SYN that you receive on which you are not listening, right? So you have one port 80. You can start replying with SYN-ACK to every request that that is basically has a fast scanning fingerprint, and you can drop the SYNs that are coming for scanning your actual infrastructure. So you can absolutely do that. Yes. Any more questions?
Hi, thank you. Hi, thank you. That's a great presentations. So my question is, like, since you walked through the OSI model, have you seen value in combining passive TCP/IP fingerprints, layer 3 and 4, with TLS fingerprints, layer 6 and 7, to improve detection accuracy, especially for stealthy scanners or C2 traffic?
Yes. I was afraid that this presentation was too long. So you can absolutely combine TCP fingerprints with TLS fingerprints. For example, you can use wildcards in both JA4 and MuonFP, and you can say, hey, if I see something from TCP stack that is kind of weird, which is non-standard fingerprints, very low MSS, no window scale size, or very small window size, and you see something like, hey, in J4, there something like with cipher count, where you have the value that is just counts the number of ciphers supported by the client. If it's very high, you can start dropping those connections. So you can absolutely do that. For example, in J4, you have just up to 99 cipher supported cipher algos, right? But what we have seen in the wild is that some attackers try to be funny and they support or advertise that they support like 150. So in J4, it will be like just 99 because it's capped at 99, but it means that is something weird because normal clients and normal browsers, they support like 20, 25, 60, but once you go very high, you can start say, okay, this is weird, and then also you see that, hey, this is TCP fingerprint is either very weird or is an IoT device, and you can start dropping those connections. So we can absolutely combine that. Now, with that said, I think we have just 2 minutes. We're also doing a network recon workshop, which is in person on Thursday, May 1st, where it is basically a two-way conversation where we can have deeper talks about specific parts of network fingerprinting. So feel free to check it out. And then there are 2 codes for Q&A and feedback.
Hey, thanks everyone. And that wraps it up. There is a happy hour, I believe, starting. So if you want to make your way out, and they are showing movies tonight, so we do have to clear out the theater. So I'm going to start herding you all out. Thank you so much.
Thank you very much. And thank you. And if you want cool stickers, just find me.